Okay.
Morning, everyone. Welcome. All right. So it's my great pleasure to introduce our second keynote speaker, Professor Ken Brown, who's the Michael Fitzpatrick Professor of Electrical and Computer Engineering, as well as a Professor of Physics and Chemistry at Duke University. So I've worked with Ken for about 20 years, and I will say that Ken has the most complete view on quantum computation of anyone in the field. Ken started his career as a chemist and then started studying quantum information theory, then became an experimentalist building trapped ion machines, and has brought it all together, leading several large projects that have really pushed the frontier of quantum hardware and quantum software. In the last few years, quantum research has grown significantly in our community, and quantum machines have made tremendous progress. Now is a great time to look to a more scalable and fault-tolerant future for these machines. I can think of no one better to share his vision of that future than Ken Brown. Join me in welcoming Ken.
Thanks, Fred. Yeah, it's a real pleasure to be here at ISCA in person. I was thinking about wearing my ISCA 2018 t-shirt, like the yellow and red. But I'm really happy to talk to you about quantum computing and its connection to architecture. I'm at Duke. As a disclosure, I should say that I'm a science advisor for IonQ. And at Duke, we've just launched this Duke Quantum Center. Okay. So first things first. Yeah, okay, so what is a quantum computer? So I think it's pretty useful just to think of a quantum computer as an accelerator. So just like you have GPUs, we can just think of a quantum processing unit, which is still controlled by some CPU. And what's special about the quantum processing unit is that it processes information using the laws of quantum mechanics. There's a really nice report from the National Academies in 2019, which sort of goes through the, yeah, actually, I think it's a really good perspective. It's not too hype-like. It has all the details of what things look like in 2019. And you can see here that, you know, there's a huge back server, classical computer server. There's some real-time classical computing doing control, which then controls these classical electronics, which then finally gets to the tiny bit, which is quantum. So when you run a quantum computer, like where you draw the line between the, between the classical computer and the accelerator is a little weird. And there's plenty of, classical work to do in this space. So of course, if it's an accelerator, what does it accelerate? And so quantum computing really started with Shor's factoring algorithm in 1994. There was some work before then, but by showing that a quantum computer, if it could be built, could break a lot of public key encryption schemes, of course, got everyone very excited. The thing that people thought about before that a little bit was quantum simulation. There's a lot of work on problems with symmetries, optimization, linear algebra, unstructured search. And actually, there's a really nice website, quantumalgorithmzoo.org, which goes through all the problems where people expect there'll be some acceleration from having a quantum computer. My own interest, having come from the background as a chemist, has always been getting quantum computers to solve hard chemistry problems and mathematical problems like that. And I think a lot of people don't appreciate how much of high performance computing time is actually spent solving quantum mechanics problems. So this is, from Argonne's Leadership Computer Facility Report. It's million node hours for their various devices. And it's hard to tell, they just break it out into chemistry, energy technologies, material science, and physics. But a lot of those problems in the end are quantum mechanical. So I think you could conservatively say at least 10% of these high performance computing time is spent solving quantum mechanical problems. And it's probably could be up to 40%. So how does it actually work? So we're not really going to worry about that too much in this talk, but just to give you a brief idea on how things are different. So this is kind of a very simplified vision of what a classical computer is. So inside your classical computer, you have a bunch of bits. That's the state of your classical computer. We'll just call that bit string A. Anything your computer does effectively maps bit string to another bit string. So I can think of it as a function, right? A function takes bit string A and outputs bit string B. This last part we never think about, but basically we can of course read out the bit string and preserve the bit string. So we can back up our computer to the cloud, we can take an image of the disk, we can do all this stuff and just keep that. So now I want to contrast that to how a quantum computer works. So a quantum computer, the state of the quantum computer is a complex vector of unit length. All right, why does a complex vector of unit length have to do with computing? What we do is we can pick a basis and we choose that basis to be bit strings. So we can think of the state of the quantum computer, psi, as being somehow two bit strings, A and B, with these complex coefficients. The operations are actually just rotations in this vector space. And so we can take this state, which is complicated, and actually just rotate it back to a bit string, which is equivalent to some classical computer state. And for readout, we can change the state. So for example, for this state psi, if we read it out in the computational basis, with probability CA squared, we get the bit string A. Probability CB squared, we get the bit string B. And then our state is actually updated to that classical bit string. And so I would have to say, like at first glance, it's unclear how this can possibly help you, right? And it's actually the inventiveness of people like Peter Shor who show that you can actually do things which are really, really hard classically that gives us all this hope in quantum computing. If you would like to learn more, I really recommend our Expeditions in Computing educational materials and resources. Here's a nice picture of Diana Franklin with Peter Shor, next to a picture of Peter Shor drawn in one of the zines that you can download from this website. We also have links to when we did tutorials at ISCA in 2018, where you can go into much more detail into how this actually works. But that's, to me, this is like the fundamental difference between these two types of devices. So now that we have a definition of the device and we have things we'd like to accelerate, yeah, why are we not accelerating? And so the problem is quantum computers are still not great. So we have maybe up to hundreds of qubits, thousands, depending on the type of device you're thinking about. The problem is the operation error is kind of limited to be 1 in 1,000. And so all the algorithms we can do live somewhere inside this kind of triangle of the now. And these algorithms where I know that I can guarantee that the accelerator will really help, such as breaking RSA, simulating these molecules, doing these physics models, they live far away from that. Now, there's a region nearby where all of us hope there'll be some cool stuff, but it's very hard to prove in that region. And so how can we get out to these hard algorithms? So again, as a chemist, I'll just pick this chemistry algorithm. So I heard, so you may have heard Christopher Savoy talk about it a while ago. But one thing that people are very promising about is building quantum computers to try to make better catalysts, which affect everything from food production to making plastics to everything. And so the original estimate in this 2017 paper was they needed about 10 to the 15 gates, which you can kind of think as being this 10 to the minus 15 error. Since that time, there's been a lot of algorithmic improvements which shifted the problem to somewhere around 10 to the minus 12. Now, the number of qubits is actually quite small. It's just 100. So if we could just somehow get 100 qubits at this error rate, we would be in great shape. So you could imagine okay, I'm just going to go in and I'm going to make my controls that are controlling this quantum system as good as I possibly can. But my estimate is that at best, that is going to get us to about 10 to the minus 6. So this is still very important, but it's not going to get us all the way out to here, right, to a trillion operations. We can, of course, work on making these problems more solvable by improving the algorithms. Now, there's kind of a cool, interesting problem in this downward slope here, which is that probably we can simulate quantum computers with 50 qubits. So if we make the problem too easy, we also kind of get rid of the use of our accelerator. But that's actually a great result. It means we can actually run problems we care about on our current devices. But there's also kind of a limit on how, there's always like a minimum number of steps you need, and that will sort of lead to this barrier here. All right. So the kind of basic idea we have is we'd like to scale up the hardware so that we're no longer limited by the number of qubits. We apply quantum error correction, which then allows us to basically get to logical qubits that are about the size of this problem. And yeah, and that's the goal. And so let's think about the other main accelerator we know about, factoring. So there's a really nice paper in 2020 by Gideon Akera, which said, okay, let's say I want to factor a 2048 bit string. That only takes about 10 to the 10 logical gates, which is actually much simpler than these chemistry algorithms. The number of physical qubits they calculate is like 20 million, but the time it takes to do this is only 8 hours. And that is like incredibly, incredibly, incredibly fast compared to anything you can do classically, in which it would take, I think, thousands of years. So that's the promise. That's the real promise of the accelerators. And then the question is, how can we do this scaling, and how can we get this error correction to work? Okay. So now the flip side is, unlike, all of us, our laptops, our cell phones, our, Frontier and Summit and all these computers work on silicon. So one of the challenges in quantum computing is that no technology has decisively won yet. And as a result, it's sort of hard to target. It makes targeting the hardware quite interesting, actually. So early quantum computing experiments were done with nuclear magnetic resonance machines. There are still a few people working on this, but it is mostly moved towards kind of educational things. There are like educational companies which will sell you small NMR quantum computers. Photons, neutral atoms, atomic ions, quantum dots, superconducting qubits are all very, which includes silicons, dopants and silicons, are all very worked on. This isn't all possible technologies. All of these technologies have at least one startup company. Most of them have 2 or 3 or 4 startup companies. And then, IBM and Google are also, working on these superconducting qubits. Honeywell was working on atomic ions, but they spun it off into a startup company, Quantini. So why are all these choices? So in some sense, the community split into what I would call atoms and photons versus the solid state. So atoms and photons are really nice because every atom is the same by nature. So the quantum fabric is not due to like manufacturing. It just comes from nature. It has really weak coupling to the environment, so the quality of gates can be quite good. The challenge is, how can we control and confine large numbers of these things? And for ion traps, for example, in this paper, some colleagues, we talked about all the ways things can go wrong. In the solid state, every qubit is the same up to manufacturing defects. There's stronger coupling to the environment because all of the qubits live embedded in this environment. And then you can print as many as you can fit on a chip, right? But if you take this, actually, this is a silicon germanium architecture, I think, with electrons in these quantum dots, and they've chosen to print 6, right? So there's real challenges in this printing, although it seems yeah, somehow from a computer science perspective, it seems more like a computer chip, what you like to do. So, so just focusing on two superconducting qubits and trapped ions. The qubits in a superconducting qubit is some connection of superconducting wires and these tunneling Josephson junctions. The Josephson junction is the part which, kind of really pushes the quantum side of things. Atomic ions is the internal state of atoms. 1 qubit gates are controlled by microwaves or lasers for ions. 2 qubit gates, there's capacitive coupling, inductive coupling, photon mediated. Trapped ions, either microwaves or lasers again. Quantum simulators and annealers. So this D-Wave company has like a huge annealer with 5,000 qubits. The largest ion system is about 300 qubits there. For universal quantum computing, there are about 55 qubits at Google and USTC, 127 qubits at IBM, 20 qubits at at Duke and Innsbruck on the academic side, Quantinium, which is a startup company, 30 qubits at IonQ. And then there are these public cloud processors. Alpine Quantum Technology is a company related to Innsbruck, where you can go in and you can pay for time to try out these devices, right? Some of them have some free devices, but you can also, pay. So I wanted to say a little bit about the quantum level material of these devices. Okay, so for superconducting qubits, the basic idea is you have an oscillator, an LC oscillator. You can imagine, like your electronic digital watch oscillator. And then what you do is you replace the inductor with this quantum Josephson junction. And that leads to the current state of the art of used by most quantum computing groups using superconductors, which is the transmon qubit. Now, what's interesting is if you look at this 2010 review of ways to build different superconducting circuits, transmon is not on here. Transmon was invented in roughly 2006, 2007. But by 2010, it hadn't really shown the promise. And so what's amazing is the transmon between somehow 2007 and about 2012 overtook all of these competitor technologies, which from a large perspective are just called superconducting qubits, right? So there's a lot of space even within that space. And so in fact, in this paper from Will Oliver's group at MIT, they look at kind of transmon, transmon-inspired, slightly different architectures for the quantum part of these devices. And they have different sensitivity to different types of noise. And they actually, I think transmons have really become dominant, but I think we're seeing, at least at the academic level, people think about how can we move away from them a little bit? Can we make a device which is like a little bit more insensitive to these noise? So what's great is you can just print them. So here's some pictures from Google and IBM where they print the qubits here at UC Santa Barbara Google. It's these like pluses. And then, and then here you can see them is these boxes at IBM. You need all these readout wires to do measurement, and you need some other wires to do control. So now that they have many qubits, they no longer show us pictures of the device. They just show us these cartoons, right? So here we have a bunch of qubits connected by couplers in this Google Sycamore chip. Here's a 53 qubit Rochester device, which is circles and lines. So there's been real progress in the size of these systems, and it becomes competitive enough that people begin to hide their design. All right, so for atomic ions, the quantum piece is a single atom. So this is an image of 1, 2, 3, 4, 5, 6, 7, 8, 9 atoms. And these atoms glow very brightly, so they're very easy to measure. So measurement in ion trap quantum computers is quite good. The type of ion, people use many different types. And one thing I find really fascinating is that all the startup companies in the US use ytterbium or barium, and all the startup companies in Europe use calcium. So is like the calcium better in Europe? Is the ytterbium better in the US? No, they're the same everywhere, right? And so it's again an example of like, no, all the ions are sort of equally good. So people can't quite agree on what the best ion is. We've been working a lot with ytterbium. We work with these kind of ion chain quantum computers. We use, what's nice about ytterbium is the laser we use for control is the same laser people use to make masks to print computer chips. And so that laser is quite cheap. And actually multiplexing the laser is also quite cheap because it's all built to build regular computers. Yeah, so we work on this. We use these microfabricated traps from Sandia National Labs. This is the last generation, the Sandia high optical axis trap. And we can imagine, we can move the ions back and forth to use different zones to have different kind of architectural components. Yeah, and so I'm leading this large STAQ project. The quantum error correction work I'll talk a little bit about, funded from this IARPA Eureka project. And then we collaborate closely with the Sandia Q-Scout program, has also a quantum computer, an ion trap quantum computer, which is available for you to apply to use, but it is not widely available. So watch out for those applications. All right, so back to this report. So 2019, one of the great things about the report is they have a long list of like where you want to get to. And they just say, we're just here. Like we haven't, like we're just at the, we should be at the bottom of this plot, of course. And what's been amazing is in the last 3 years, we've made some real progress. So this first thing is just showing a any quantum algorithm, which really pushes the limits of classical computers. And so it's called quantum supremacy, meaning that the quantum device runs way faster. It's the first example of an accelerator. And so Google showed this with 53 qubits in 2019. And then USTC in 2021 showed it with 56 superconducting qubits, which is great because, you know, from my perspective, science is about repeatability. And the fact, you know, more than one group can do these things is very important. But also it's an example of, we have this accelerator, but the outcome is just random numbers. So we sort of, it's not the accelerator we want. We'd like to get to quantum error correction. And we're not quite there yet, and I'll talk a little bit about our experiment in a bit. But what's amazing is in the last 2 years, many groups have become very, very close, very close. And I think that's amazing because in 2019, no one was close, right? That's real progress. The next thing has to do with these hundreds of qubits. So, you know, IBM has now released their 127 superconducting qubit Eagle processor. And then in kind of a new, I don't know, Rydberg atoms, which have been around for a long time, have recently been doing kind of amazing things with doing simulations only, but in a way that's compatible with gates, using up to 289 qubits, right? So that's really quite amazing. So the question is, of course, how can architects help? So I decided to go to DBLP and look at all of the papers in ISCA, Micro, ASLOS, and HPCA that I could find using quantum. So what you'll notice is there's like this initial burst here. And I really think, you know, there were some people who were out on a limb looking at these things. And actually, this is when I met Fred. And what I found really amazing about this period was, from a physics perspective, you're just trying to make the thing work. And then Fred and Kubi and Mark Oskin and Isaac Chuang said, okay, let's imagine everything works. Can you actually make an architecture? And in this first paper, the answer was actually no. It turned out that the pitch of the wires you needed to control these devices, people hadn't made yet, but were working really hard to make, wasn't really compatible with the control. The second thing, which was really nice in this paper and really fleshed out in this period, was the cost of communication. One challenge in the quantum computer is you just can't copy things. And so any information you want to to connect across your computer, you actually have to move. So that cost of communication and the need for this idea of quantum teleportation, which is kind of a way to like you pre-make wires, basically, you pre-make the communication channels. Those things have survived and are really critical to like our future architectures. Okay, then there's this period here, which I sometimes actually refer to as the first quantum winter. And unfortunately, I was an assistant professor during this time, which is not the best. A few of us survived the winter. And actually, these two papers in 2013 and 2015, I'm a co-author with Fred, and then in the second one with Diana Franklin and Margaret Martinozzi. And then suddenly there's this explosion. So what causes this explosion? So I think the first order thing is really IBM in 2017 releases this cloud quantum computing availability to everyone, the IBM Quantum Experience. Second thing is Google starts their quantum project in a really large way. And then the third thing is I think our ISCA tutorials in 2018. It must be, right? This is kind of this massive bump. All right, so what could architects do for us? So the first thing is, of course, physicists and maybe and sort of low-level engineers don't think about all the ways the optimizations connect together. So in this really nice paper from Margaret's group and then Norbert Linke, who is running the University of Maryland Trapped Ion, they looked at how qubit mapping and scheduling and native gate operations can all be compiled together to improve things. And what was great is they showed improvement on two available cloud devices, the IBM device and the Rigetti device, which are both superconducting qubits. And they also showed a modest improvement on a more modest improvement on the Maryland device. It's still 50%, which is great, max. And that's because the ion traps have kind of this all-to-all connectivity, and and on these devices, there's more worry about routing the information around. So what I found interesting about it was thinking about, okay, I want to build this device, and I have like different kinds of users. So ideally, I want to get to the point where it's just an accelerator. And in that case, I really only care about the final result. So the user will input the algorithm as some sequence of quantum channels, like that's pretty low level already. And then the compiler basically can do anything. It could even say, okay, actually this thing is small enough, I'll just do it on my classical computer. Like I don't need to do it, right? But that kind of interface kind of limits what you can do. But that is basically sort of the interface that last paper was working with. So you could go a bit lower and think about, okay, I want to optimize these circuits. And so input should actually be machine operations on specific qubits. And then there's a question of whether a machine operation is a gate, or is it actually like a physical electronic signal, like an RF pulse? And then this question about like error suppression that we can do through things like dynamic decoupling, should that always be on, or should it be something that the user has to specify? Like what's the user's involvement there? And then the last thing is like people I think of as basically a machine tester. So you want the lowest level access possible. And then the thing that I am unsure of is whether or not that's reasonable for users. Like how do we give them enough information to work with that? Okay, so one thing that I work on is we build these ion trap quantum computers at Duke. It's part of the STAQ project. Our goal is to build a 32 qubit device. At present, we just have a few qubits. We've had a lot of, you can talk to me later about supply chain issues during the pandemic and why it's better to be a theorist or do just computer work. And then, and then we work closely with this expeditions in quantum computing. Yeah. So but part of this work, we work closely with Fred's group and again with Margaret's group, and really see that a lot of kind of architectural questions really push people towards this machine tester level. And I actually think that's someplace where academic quantum computers can provide an advantage over commercial quantum computers, because maybe we can make that possible. So as an example, we control our quantum computers using ARTIC, which is an open source programming framework, which allows you to control FPGAs using Python. They come in these nice racks you can buy with some easy cards. What's nice is that it is really good control. It looks like Python. It's not exactly Python, but it's been great for me and my students. I also like it because there's kind of a large community. It started at NIST in the ion trap group, so it's mostly been adopted by ion trappers and neutral atom people, but it's across the world, in Europe and in Asia. We've been working on an open source project called Duke Arctic Extensions because my students just gave it a boring name. But I just want to give you an example of something we can do, which I think is impossible to do on a commercial quantum computer unless you work for the company right now. So let's say you want to run a quantum circuit, but you're worried that your 1 and 2 qubit gates are not well calibrated. And those both rely on some actual physical layer calibration, which could be laser intensity. So we can write the flow of this information according to this directed acyclic graph. And then we can actually create an automated engine which basically checks through these nodes to see if these calibrations are out of date, and then appropriately updates the calibration before running the next job. So one challenge on current commercial devices is you don't control when they calibrate. So you start to run your quantum algorithm, looks great, calibration gets kind of like not so good, and you don't really have the opportunity to fix that. So what's interesting is we implement this Optimus algorithm, which is in this paper from Google, but I think that's an interesting place to play. So our goal is to try to make this kind of device for all of you, to think about what kind of optimizations can be performed even at that level, so that and then I'm sure if we find good ideas, the companies will pick them up. The next thing I like about working a lot with architects is physicists have like really strong opinions. So in ion trapping, there was like a real disconnect between, should ion chains be 2 or 4 ions, or should they be the longest possible chain? So that on the side of 2 or 4 ions is basically the quality of ion gates is much better when you have these small chains. When people think about the longest possible chain, the goal is that you just have a larger computer, basically, right? So these two teams basically argue with each other all the time about like who's made the right choice here. And so it's nice working with Margaret and her student Prakash and my student Dripto. We basically said, well, obviously there's got to be something in the middle. So we looked at all these 64 qubit algorithms. We looked at the size of the ion chain, the topology of the ion trap, different pulse forms, which are kind of microarchitecture. And then what's interesting is that you actually get different choices for different algorithms. So in our current era, like we just need to optimize everything to get the best possible performance. So looking forward, I want to try to work on this axis, right? So we want to scale the hardware and then have this quantum error correction. So I'm going to briefly, okay. My plan is the following. I'm going to remind you of the simplest classical error correction code. Then by analogy, I'm going to introduce the quantum error correction code, which that's the big jump, I think. And then I'm going to explain a little bit about the work we do in that space. And then I'm going to switch back to the architecture part. So imagine you want to send a 0, and 85% of the time it works, 15% of the time the bit flips. And let's just make our lives easy and imagine it's a binary symmetric channel. So the way classical error correction works is I just repeat things. The simplest one is I repeat things. So I repeat 3 zeros. So if 1 bit flips, I can fix it with majority voting. I have to send each bit through the channel, so every bit could flip independently. And then at the end of the day, I get all these possible outcomes. And what I see is that the failure rate of getting the correct message after doing majority voting increases relative to a bare bit if the probability of these lines failing is less than 50%. So 50% is a threshold. After that, you can still use it. You just have to assume everything flips. And so, for example, if the probability of failing is 15%, then when I put this together, now the probability of the logical bit failing is 94%. I find it a little more useful to, instead of to think about the two code words. So I have the all zeros and the all one code word. If one error happens, I'm still in a completely disconnected graph. And if two errors happen, then I'm messed up. So what we see is that we can correct a single error, we can detect two errors, and three errors ends up being a logical error. It maps code word to code word. So we call that the distance, D. So in quantum computing, the main problem is we can't copy. So we also want to preserve a superposition, so we can't take the majority vote. So here we have this quantum state. It's just 2-bit, right? It's a superposition of 2-bit strings. Now the first bit flips, which I represent by X here. And I want to keep those coefficients, but still fix the problem. So if I do a majority vote, I just collapse to either the 100 or the 011, and then I don't keep the superposition. So what's nice is if people who do error correction, they think about things in terms of parity checks. So actually, what you do is you can just check the parity. So the parity between these 3 bits differs depending on which bit flipped, but it does not depend on the content of the message. That's the basic idea. So we can do quantum error correction because we can not ask what is the message, we can ask about these parities. So I'm just going to rewrite it in this kind of graphical language. So there's my 3 bits. One of them flips, and then that parity, which is represented by the line, is broken. And then I know that I need to fix that top bit without ever knowing what it is. And so we can, I think about it as these blocks. We'll just ignore these Z's. We don't really need them. And so we just measure where we've been, and then we go back. Now, naturally, error correction is not magic. So if 2 things fail, we do our parity flips and we have this logical error. So now imagine we want to suppress higher weight errors. So we can do it in 2 ways. We can take our 3 bits, make them 1 bit, and then take 3 of those bits. And that leads to these higher weight parity checks. And then I actually do like the connection between error correction and types of different ways to do voting. So this is kind of like a council of representatives model. This neighborhood votes for their legislator. The legislators get together and vote. Or I could just put more of them in a string. And this is like, there's no hierarchy. It's just like direct democracy. Now, of course, we're going to have more errors. And so in the case of this line of it's just a repetition code, when I put it out as a line like this, if I have bunched errors, I only see these parity checks at the end. And so I can build a decoder, which basically just looks for the minimal weight between these parity edges. Okay. Now, the nice thing about this classical error correcting code is that it's already been implemented on quantum computers. So this is an example from the first Santa Barbara Google team and then Google team. So in 2015, they showed that you could do classical error correction and that it increased the time that you could preserve. You could preserve the information. And now, more recently, they've been able to do it up to a distance of 21, which is quite large. Now, for quantum code, the challenge is you have more types of errors. You have bits flips, phase flips, and you can flip both things. And so you could imagine, well, what if I have parity checks, these Z checks that look for X errors, or these X checks that look for Z errors? Then you could imagine, okay, an X error happens here, it flips these E checks. A Z error happens here, it flips these X checks. A Y check happens here, it flips both X and Z checks. And it looks great. It looks just like a repetition code. But there's something broken with this cartoon. And I'm happy to talk about it later to anyone who's really interested. But the key thing is we can fix it by making different checks. So these checks are slightly more complicated. This is the 913 surface code. It encodes 1 logical qubit into 9 physical qubits, and it has a distance of 3 against X, Y, or Z errors. It has exactly the property you want, and that allows us to see these X errors and fix them, see these Z errors and fix them, see these Y errors and fix them. So yeah. So there are actually many error correcting codes. The first error correcting code, also by Peter Shor, fits in this model of starting with this kind of simple idea and mapping it here. It's not how we derived it. The surface code, again, as we just saw, I can think of taking these small checks, putting them together and get them here. And then that paper from Dave Bacon leads to this sort of Bacon-Shor code. And so surface code by far is the most popular quantum error correcting code right now. It just makes a nice checkerboard of checks, X checks and Z checks. Bacon-Shor code is kind of out of favor because the basically there are very few checks, but the threshold is quite bad. And so if we can't do it by just making this thing longer and longer. All right, so then I guess just as an idea of how I do research. So I'm having breakfast and I'm like, okay, on the one hand, this vegan bacon just reminds me of like a Bacon-Shor code. I have all these nice strips of bacon. And then these waffles remind me of the surface code. And the way you decode the surface code is just like that repetition code, is I want to find little checks that connect between these two parity errors. And so then I was like, okay, well, these two codes have very different properties, but what are the codes that live in the middle? And so the way I think about it is you have this string of errors, and it's trying to sail from its pirate base to attack the port city or whatever. And if it's just Bacon-Shor, it can sail through very easily. So I want to add these icebergs of surface code, which basically prevent it from getting to the other side. And what I wanted to ask was like, how many icebergs do I need to make this thing work? And so what we found out was that actually you do need kind of a linear number of these icebergs, but there's a huge family of codes. And it also enabled us to find new ways to build decoders and just build on these things. And I'm super excited about it because actually these sort of compass code models are the current error correcting codes that are happening. So IBM just has this nice heavy hex code, which we can map back to that kind of compass model. 913 surface code, of course, is a compass code. This is from the group of Andreas Walrath at ETH. And you see that because they're superconductors, they have these kind of linear connections here. I would like to look at something that takes advantage of the ion chain and this all-to-all connectivity. This is work done with Chris Monroe's group. I want to say it was actually really, all of the data they got during the pandemic when they all had to work at home. And it's a testament to the system that it's just kind of automated and they dialed in and did their experiment. Basically, it's interesting because ion qubit always looks like a linear chain, but the topology of connection between the qubits is all-to-all. So we can have these like single ancilla connect to all 6 of these qubits and back and forth. And so just to show a little bit of data, we compared 2 different ways to prepare the logical state. The one called not fault tolerant, the other one called fault tolerant. And then what I want to say is that fault tolerance always assumes you have an error model. So what this experiment is testing is like, is our error model reasonable, right? So if our error model is reasonable, fault tolerance will do better. If it's not, we could get basically the same thing. So what we see is we prepare these 2 states. We compare the ideal measurement versus what we measure. So the ideal measurement varies between 1 and -1. And we see that this fault tolerant preparation, even if we don't do any correction, helps. When we do correction is where it shines, and we get actually quite low errors doing correction at the measurement end. And then if we do detection where we throw out anything which shows an error, for the fault tolerant system, we just saw no residual errors. So it tells us our model is quite good. There's been more work outside of Compass codes, really nice work from Honeywell Quantinuum on a STAQ code, use repetitive measurements. The first experiment showing repeated measurements to do a full quantum error correction code. There's some really different ideas based on bosonic encoding from Yale, where they've also shown the ability to do two-axis coding. And as I mentioned, this is just a repetition code, but I think it's great that they're able to go to this quite large distance. So everybody tells you, okay, you need 1,000 qubits per logical qubit. Where does this number come from? Comes from a simple calculation that the physical probability divided by the threshold raised to the power of half the distance. You can estimate your logical error, and then you say, okay, what do I need? And the problem with the surface code is it's a great quantum code because the threshold is quite high. It's just a little bit below 1%. But it's a bad quantum code in that the distance does not scale well with the number of qubits. So, so what we need to do is think about scaling. Basically, 10 years ago, there are a couple key ideas in terms of photonic interconnects building up these devices and junctions in terms of, just for ion traps, building up these surface ion traps. And they've not, the shuttling has begun to pay off for sure. But overall, these schemes have not yet outshone just putting a lot of ions in a chain. To do further integration of devices, for ion traps, we need to think about how to get our controls there, how to get the optics there, how to get the microwaves there. And then once we've done that, then we get to the real problem, or we get to the next problem, which is how can we actually decode this thing? And so this is an example of a much larger surface code. The red dots are the actual errors, but you don't get them. You get these parity mismatches. And your job is to match them. And so your decoder has to decide between these two choices, which both look pretty reasonable for matching these errors, where one fixes it and the other one doesn't. But it's worse than that, because in a quantum computer, you can't trust anything. You can't trust your gates, you can't trust your measurements. And so you have to worry about these 3D kind of, basically this 3D matching problem. And all these images I borrowed from Guillaume Duclos-Yancey. So, in this ISCA paper from Fred's group, they actually point out that as these things get hard to calculate, effectively you're slowing down the rate of your quantum computer because you may not have been able to decode it before you have to make your next decision. And that has led to some really nice work, for example, from Microsoft and Georgia Tech, where they say like, well, what is the microarchitecture which is fast enough to keep up with the rate of superconducting qubits so that I can actually decode this thing? And maybe you sacrifice a little bit on not having the ideal decoder in order to have a microarchitecture which actually can keep pace. The other thing I would just want to point out is that, again, surface code from a classical perspective is a bad code. And we should think about moving to codes which are finite rate. So for example, this is a surface code that this is a surface code here. It takes 450 qubits. It's on a torus, so there's 2 logical qubits, and it has a distance of 15. But if I allow kind of not nearest neighbor interactions, which are represented by these kind of L-shaped red and blue checks, then I could have the same number of physical qubits, now have 98 logical qubits, and I pay somewhere, right? So I pay in the distance. So there's been a huge amount of work on finite rate codes in the last 2 years. But one paper, which I think is very kind of accessible, is this thin planar paper from Microsoft, where they basically say, if I allow myself to have not just a planar connection of qubits, but a stack of qubits, then I can actually get to a point where I only need kind of 50 qubits per logical qubit to get to the error rates I need. So to sum up, yeah, future quantum hardware, my opinion is that right now, scaling is the current challenge. Any ideas you have to help us scale, I would love to have. I believe we're going to have to move into some kind of modular architecture. So connectivity is a key challenge, and how to work around kind of small bandwidth, like small rates, and how to beat it with maybe time-space multiplexing to get the bandwidth up, it's hard to say. I think we'll start also moving to heterogeneous systems. It's kind of interesting to me because there is this ISCA 2006 paper on quantum memory hierarchies from Fred's group. But I think we, even at the level of kind of taking advantage of, say, for example, the diversity of superconducting qubits or the diversity of ions. And then finally, I think this kind of back to the beginning to say, okay, if I want to make a finite rate code architecture, what are the pieces I need? And if I write down for you, like from a physics perspective, this is the best we can hope for, I would like to know, does it still work? Yeah, and so then, oops, hopefully advance. Yeah, anyway, so that, I didn't talk too much about our work, so please come to our website, find more. This is our opening of our Duke Quantum Center with everybody. Yeah, Robert Calderbank, Eamon Marvian, Kristen Noel, Marco Cetina. I'm really thankful for all my collaborators. I'm really thankful for Fred and Diana and Margaret for getting me involved in the architecture community. And then we also work on a bunch of stuff, other stuff. So anyway, thanks for your time, and I'm happy to take any questions.
So please come up to the microphone if you have any questions. Let me start off with one. So Ken, you talked about the future with error correction and fault tolerance. I was wondering if you might say something about how we might combine some of the things we're doing today, like sort of error mitigation, dynamic decoupling for current machines with error correction.
Yeah, so so first off, I think dynamic decoupling for sure will connect directly with error correction. I think there'll be kind of a real, like a really happy marriage between those two kinds of ways. Dynamic decoupling and quantum control to get the errors lower, and then error correction to drop it algorithmically lower. I think with terms of the error mitigation part, there will always be some errors. And that error mitigation will always help us get the better measurements we can out of the devices we actually have. So I do think they will move forward into the future.
A very simple question. The first equation you showed, bracket psi is equal to complex sub A, complex sub B. Are the A's and B's bit strings?
Yes.
Are they connected to the number of qubits your computer has, or something else?
Yes. So the quantum computer will have a finite memory, basically.
Yes.
And so the size of the bit string will be determined by the quantum computer.
So memory is a kind of a quantum gate or a quantum qubit.
Yeah.
What
so
is
the
connection between the bits and qubits? That's what I was missing.
Oh yeah. So that's a great question. So the difference between a bit and a qubit is a qubit can support being in the superposition. So I can't write down the CAA plus CBB if I only have bits. So but the qubits in the end represent bit strings. Okay, so A's and B's are the qubits. So yeah. So for IBM, for example, 127, the A and B's are 127 element bit strings. Yeah. Made of qubits. Yes.
Thank you. A great talk. A quick question. So I know you are mainly focused on hardware for this talk. You also mentioned quantum winter, right? So I guess going forward, my question is, in addition to hardware scalability, what are the other main challenges you think for may cause the next quantum winter, for example, commercial readiness, user accessibility. You mentioned all these. I just wonder if you can have a short list of the main challenges in addition to hardware itself.
Yeah, I think I just put up this slide. So the error correction, this error correction plan is like very long term, right? We have to get from hundreds to thousands of qubits, right? And so all of us hope, I strongly suspect it will be true, that in the thousands of qubit regime, with errors of around 10 to the -4, say, there'll be new algorithms. But the hard thing about those algorithms, it's like they're very hard to prove there's something there. Does that make sense? And so I think finding good algorithms in that regime is one thing which will really help us avoid the next quantum winter.
Moin Qureshi, Georgia Tech. Ken, excellent talk. I really like the way you communicate, right? So 2 questions. First, how do we do a better job of making quantum computing seem less scary, right? Because in my view, that is really one of the big challenges in tapping a lot of creativity and research that's available, but just people don't want to come near it because there's a high barrier, right? Go ahead.
Oh, well, okay, so I don't know if any of you participated in the I2 Kin Quantum, which I guess we did last ISCA. That seemed quite successful. We took in people who hadn't really done any quantum stuff and actually produced some interesting results. I think one thing is that I just want to emphasize a lot of the problems we have are just classical problems. They're just classical problems applied to the quantum domain. And so the amount of quantum domain expertise you need to actually help make progress is probably not as big as you think. Of course, you need to talk to someone to make sure you don't break any fundamental rules, but I actually think it's not so far.
Okay, quick research question. As we learn more about the hardware in this, we could do a much better job in the software, right? In fault tolerance, we still deal with like uniform error rates and so on and so forth. As we learn more about the hardware and non-heterogeneous, non-uniform error rates, what will that imply for fault tolerance?
Yeah, so I think well, actually, I have a few examples where it really helps fault tolerance. The example that comes to mind immediately is there's a nice paper looking at neutral atoms where you convert your errors into erasure rates errors, and that makes fault tolerance much cheaper. In some of our own work, we looked at the fact the errors are actually coherent, and then you actually do a slightly different circuit from the canonical circuit, and you get much better results. And then the third thing, which I didn't talk about, are these bosonic codes. So in superconducting qubits, in some sense, the microwave cavities are kind of the best thing. So if we can put our quantum information into the microwave cavity and store it there, that's better than maybe doing circuit error correction.
Great, thanks.
Sure.
Hi, I'm Raghav Pothakuchi from Yale University, and thanks for the insightful talk. Regarding mitigation of errors, currently we see that mitigating errors requires changing the algorithms and the circuits. That is the very nature of the computation that we're trying to do. Do you see that being the future, or would it be possible to make error mitigation modular and even abstracted so that we can layer and then build our architectures on top, similar to somewhat what we do with the classical systems?
Yeah, I think as we get better at building these devices, I believe they'll become more homogeneous, which will allow us to mitigate blocks and then connect the blocks. So yeah, I think we will get to that.
Thank you.
Hi, thank you for your talk. This is Henry from MIT. So I have a question. So what's your opinion on the advantage of using trapped ion over superconducting machine to do the error correction? And do you think in the future we should build error correction code specific hardware to achieve the error fault tolerant machine? Yeah.
Yeah, so I do think we should tailor our error correction codes to the specific errors of machines. And I think we kind of saw an advantage in the way we did Bacon Shore with the ion trap, you could not really do with a superconducting qubit. You could do a different type of Bacon short with superconducting qubits, but that's an example of where we got an advantage based on machine architecture. Yeah, the reason I like ion traps still is the every ion is the same. And measurement, yeah, actually currently gate rates are quite good and measurement is really quite good. Just to be fair, my superconductor friends always remind me that it's slow. But I always, I actually want to make quantum computers that have basically exponential speedups. So I'm not so worried about that.
Thank you.
Hi, Olobi from Georgia Tech. Great talk. So you talked about Bacon short codes for ion traps, and now we have these finite rate codes, the LDPC codes coming out. One of the key challenges for those codes is that you need some 3D connections. Connectivity is less of an issue for ion traps. So where do you see LDPC codes in the on these ion trapped ion systems? And does this actually simplify or worsen the classical decoding problem?
Okay, so I'll start at the end of the question. So LDPC codes are harder to decode. The last week of the archive has been 3 papers on linear decoders for LDPC codes, which is amazing, but they're not optimal decoders, right? The next piece is, an ion trap within an ion chain has full connectivity, but that ion chain will not become infinitely large. So then I have to somehow communicate information between the chains, either by shuttling ions between chains or making photonic interconnects. And so then that graph is like kind of locally fully connected graph on a larger fully connected graph between these nodes. And what I don't know is how well LDPC codes map to that, right? So can we find an LDPC code that has that structure? Then I think would be a huge win.
Thank you.
Hi, Sudanwa AMD. Thank you for the talk. So I know very little about quantum computing, so this question may be a little naive. So in the classical error correction world, from terms of architecture design, we usually think of them as either like Hamming codes where you know the specific small number of bits to be corrected, and then like things like BCH or Reed-Solomon codes with large number of bits to be corrected, but you know what they are and efficient. It sounded to me like in the quantum world, it's really that latter bucket which is being optimized for, but is this way of sort of bifurcating error correction between like Hamming style codes versus like these block correction codes useful at all in the quantum computing realm?
Yeah, well, so I want to say that the STEAM code actually derives from a Hamming code. And then the main way that we think about doing fault tolerant computation is based off Reed-Muller code. And so we do borrow from that. I think the difference, the real difference is a lot of classical error correction is in this communication kind of perspective where you can trust the measurement. And I think the big difference in quantum error correction is we just can't trust anything. And so some of the gains you'd get for a Hamming code kind of go away when you can no longer trust the bit outcomes, for example. Yeah.
Okay, thank you.
Hi, Ramin from Georgia Tech. I have a question. Just before the pandemic, JPL launched a study in space station, and they did a quantum experiment, and they were able to achieve by 3 orders of magnitude cooler temperature in the space because of the gravity differences compared to the Earth. Do you see any opportunity for operating quantum computers on other places than Earth and be less vulnerable to noises and errors that we might have in the Earth?
Yeah, so it's sort of interesting. So I think space is very cold and pretty consistent temperature as long as you avoid the sun. And that could be an advantage for quantum computers. I think the flip side is Google has shown these interesting cosmic ray problems with quantum computers. So for that kind of quantum computer, putting it on the space station would probably be a bad plan. And you maybe would rather put it like deep underground.
Hi, I'm Kate Smith from UChicago. I just had a quick question about this idea that we have if we were to draw the Venn diagram out of all these different platforms that are emerging, they definitely have their strengths and weaknesses, which alludes to the idea that we will have heterogeneous systems. Is there something that you say we should keep in mind as we design towards potentially a very diverse set of hardware in the future for quantum?
Yeah, well, I mean, I do think, I do think some diversity of how we build these devices will be good. So as an example, even in the context of superconducting qubits, there are basically two types of qubits. There's a qubit which holds the data and a qubit which checks for errors. Currently, we make those two qubits the same. Like, why do we do that? I mean, we do it because it's easier to do in some sense, right? And so I think that's an example of where I think there can be real gains from these differences. The flip side is, so ion trap memories are really quite long relative to superconductor memories. But so far the work in figuring out how to couple the superconducting memory to put it out into an ion trap memory, there's been no gain. Like, you lose so much in that, they call it transduction. So if we could find good ways to do that transduction, I think it opens up a new world for us.
Thank you.
Great. Well, thank you, Ken. Thanks so much for coming to talk to us. So we're going to move straight into our quantum session, which is topical. And Gokul Ravi will be the session chair.